Children, in the previous class, we learnt about electric charge, its properties, method of charging a body, units of charge. In this class, we will learn Coulomb force, that is, quantum of Coulomb force between electric charges, permittivity, and relative permittivity. First of all, we should know the point charge. When the linear size of a charged body are much smaller than distance separating them, then the size may be ignored and charged body are treated as point charge. Now, Coulomb's law of electrostatic. Charles Coulomb was a French engineer. He invented a torsion balance to measure the quantity of force and used it for determination of forces of electric attraction or repulsion between a small charged sphere. He thus arrived in 1785 at the inverse square law relation, now known as Coulomb's law. According to Coulomb's law, the electrostatic force of attraction or repulsion between two-point electric charges is directly proportional to the product of charges, inversely proportional to the square of distance between them, and acts along the line joining the two charges. Since force is a vector quantity, so obviously it has a direction. In this class, we will learn or we confine ourselves with its magnitude only. Remember, Coulomb's law applies to stationary point charge only. Now, if Q1 and Q2 charges are separated by a distance r, then F is proportional to Q1 and Q2 and F is proportional to 1 by r square. If we combine these two, we can say F is proportional to Q1 Q2 by r square, or F equal to K Q1 Q2 by r square, where K is a positive constant of proportionality called electrostatic force constant or Coulomb constant. In vacuum, K equal to 1 by 4 pi epsilon naught, where epsilon naught is the permittivity of free space. Now, we should know here what is permittivity. Is a physical quantity that describe how an electric force or field affects and is affected by a dielectric medium or a material's ability to transmit an electric force or field. According to Coulomb's law, if two charges Q1 and Q2 are placed in vacuum at distance r, then the magnitude of force in vacuum is F naught equal to 1 by 4 pi epsilon naught Q1 Q2 by r square. Here see Q1 Q2 are the modulus value because we confining ourselves for the magnitude of force only. and epsilon naught is the permittivity of vacuum. The value of epsilon naught in SI unit is 8.854 into 10 to the power minus 12 Coulomb square Newton inverse meter minus 2. Now, if the charges are placed in a medium, then the force of attraction or repulsion may be written as Fm equal to 1 by 4 pi epsilon m Q1 Q2 by R square. This is equal to 1 by 4 pi epsilon naught epsilon r Q1 Q2 by R square, where epsilon m is equal to epsilon naught into epsilon r is the absolute permittivity or simply permittivity of the medium where charge is placed, and epsilon r is the relative permittivity of the medium. For simplicity, 1 by 4 pi epsilon naught is equal to 8.9875 into 10 to the power 9 Newton meter square Coulomb minus 2. This can be written as, means its value can be 9 into 10 to the power 9 Newton meter square Coulomb minus 2. Here see a new term, that is relative permittivity. So we must now know relative permittivity. Relative permittivity are known as dielectric constant or a specific inductive capacity or dielectric constant, which is given by capital K is equal to epsilon r, and this is equal to epsilon m by epsilon naught, where epsilon m is the absolute permittivity of the medium where charge is placed, and epsilon naught is the relative permittivity of vacuum. So we can say the ratio of absolute permittivity of medium to that of vacuum is relative permittivity or dielectric constant. Again, now if we find F naught by Fm, we will get its value epsilon m by epsilon naught, which is nothing but epsilon r. Again, see the formula of Coulomb force in vacuum, which is F naught equal to 1 by 4 pi epsilon naught Q1 Q2 by R square, where 1 by 4 pi epsilon naught is equal to 9 into 10 to the power 9 Newton meter square Coulomb minus 2. Now, if we substitute this value, that is 9 into 10 to the power 9 Newton meter square Coulomb minus 2 for Q1 equal to Q2 equal to 1 Coulomb and R equal to 1 meter, then F naught equal to 9 into 10 to the power 9. Now we can define 1 Coulomb charge. One Coulomb charge that, when placed at a distance of 1 meter from another charge of the same magnitude in vacuum, experiences an electric force of repulsion of magnitude 9 into 10 to the power 9 Newton. Here repulsion is because Q1 and Q2 both are of the same kind. Recall the earlier definition of Coulomb, which states a Coulomb is the charge flowing through a wire in 1 second if the current is 1 ampere. Here, relative permittivity of certain material is given at room temperature and under 1 kilohertz. Now, on the basis of the discussion, write the answer of following question. First, state the Coulomb's law of electrostatic. Second, what do you mean by permittivity of a medium? Third, two charges 5 nanocoulomb and -2 nanocoulomb are placed at points 5 centimeter 00 and 23 centimeter 00 in vacuum. Find the magnitude of Coulomb force between them. Also identify the nature of force. Remember, nano means 10 to the power -9. Fourth, what is the magnitude of force in the above if vacuum is replaced by water? We can use the value of dielectric constant of water from the table, which is nearly 80 at room temperature. In this question, can we guess the unit of dielectric constant? Fifth, identify the nature of electrostatic force between the two charges Q1 and Q2 if Q1, Q2 less than 0 and second Q1, Q2 greater than 0. Also identify the kinds of charges in each case. Thank you. Next we will get the information about Coulomb's law in vector form. Thank you.